Tonight we have the pleasure and the privilege of meeting Dr Alan Soper FRS, who from now on wants to be called Alan. Okay? He's now retired. Alan studied physics at the University of Leicester, followed by his PhD, where he was using neutrons to investigate the structure of aqueous solutions. So you've been in this business quite a long time.
Too long.
On completing his PhD, he spent time in Ontario and Los Alamos developing his skills in neutron scattering and working on the design of the diffractometer at Los Alamos. He was an assistant professor at the University of Waals, Ontario, before he chose to return to the UK in 1986 to take up a post as a staff scientist at the newly constructed ISIS pulse neutron source at the Rutherford Appleton Laboratory, where he spent the next 30 plus years of his career until retirement in 2017. During that time, in 2014, he became a Fellow of the Royal Society. Alan is probably still the world's leading expert in the structure of water and water-based solutions at molecular level. Using experimental techniques such as neutron and X-ray diffraction, combined with computer simulations and structure refinement, he investigated the organisation and behaviour of water molecules, including their interaction with other molecules and surfaces. His work has huge relevance, given the importance of water in the biochemical processes of living organisms and why water is more dense at 4 degrees. He has characterised the structure of water under extreme conditions as found miles down at the bottom of the ocean and in heavily confined water such as occurs in anoscopic mineral cavities. Alan has contributed to the design of several novel instruments and techniques for total neutron and X-ray scattering, such as the Nimrod at the ISIS Research Facility. That's it.
Okay.
I introduce Alan.
Thank you. I don't know how to respond to that, so I won't say any more. Thank you very, very much, Margaret, and everybody for the opportunity to be here tonight. I haven't got any jokes, so don't worry, I'm not going to make any funny puns or anything to do with water, because I don't have anything like that. I mean, the problem I've got is that I'm, first of all, as Margaret says, I was retired, which means I haven't actually given any sort of lecture now for several years. But secondly, the last time I gave a lecture was very much to a technical audience of people who. And so, of course, I've tried to make this lecture at a level where hopefully a lot of people can understand it. But it's quite possible that I haven't got it quite right yet, and there'll be some things I say that don't make any sense to you, and they're just gibberish, and you'll have to sort of, pull me up at the end, and make sure that by the time you leave this lecture, you do understand something about what I've been trying to say. Now, I gave Margaret the title, the Enigma, with many variations, of course, following the Elgar piece of music. But I didn't actually check beforehand that what enigma means. Unfortunately, it works out pretty well. Enigma, according to the dictionary definition, a person or a thing that is mysterious or difficult to understand. And I'm hoping at the end of the lecture you will start to appreciate why water could be classified as an enigma. Okay, so let's proceed. If this machine is going to work, go back a bit. This is a picture of a lake in New Zealand, just below Mount Cook has got it in the background here, and it's basically illustrating that we live in a world of water. All around us, we're made of water. We deal with it continuously every day of our lives. And it occurs in three forms: liquid, of course, that's what we all live in, but there's also ice around in our refrigerators and on the mountains, although I understand the problem with glaciers melting is becoming quite serious as far as climate change is concerned. And we also have vapour in the air, water vapour in the air, which condenses to form clouds and ice crystals and so on. So it's an absolutely ubiquitous material. And it's a bit odd that if you actually read the literature on water, you will discover that many scientists will call it anomalous. So how come a material which is so common all around us and yet it's regarded as anomalous? If it's anomalous, you would normally think, by the way, can you hear me all right? I forgot to ask. Yeah. You would normally say it's unusual, it's different. If it's unusual or different, then what is normal? So I'll just say a little bit about this. But if you really want to learn, sorry, I've gone too far. It's gone ahead of me. Let me just do this again. If you really want to learn a lot about water, there's a wonderful website by a fellow called Martin Chaplin at the South Bank University in London, and he's got a whole massive list of all the features, all the aspects of water. And so if you really want to learn about it, you can actually go on that website. It's got something like 5,000 or 6,000 references to different bits of work that have been done. And one of the things that he says is that water has so-called roughly around 75 anomalous properties. So although this is a very, very common liquid, it's actually anomalous. It behaves unusually. So what do I mean by behaving unusually? Well, if you think about it, this is a lake. In the winter, there's a good chance that lake will probably freeze. The ice sits on the surface of the water, so the ice is less dense than water. I think it's fairly obvious. We all see that all the time. But it's more subtle than that, because the other feature is that as you cool the water down towards, as you melt the ice, it's obviously denser when it forms a liquid. As you warm it up, though, it keeps on getting more dense. So that means that in a lake in the winter, the warmest part of the lake is at the bottom, because the warmest part is at 4 degrees C, which is the temperature at which the water has a maximum density. It's actually at the bottom of the lake, and that means life can carry on underneath the ice in the winter. And we almost certainly owe our existence to that fact. But it's very unusual, because first of all, the solid is less dense than the liquid, and secondly, when you melt the solid, it keeps on getting denser as you warm it up. So this is extremely unusual compared to any other liquid. There's another aspect which I'm going to say a little bit more about, because it's equally strange. A thing called heat capacity. I'm hoping people will understand what I mean by heat capacity, but it's a very simple concept, really. I need a certain amount of heat to warm any material up, obviously, and typically you calculate the amount of energy that's required to heat an object up by 1 degree Kelvin, 1 degree Celsius. And I've listed a whole series of liquids here: water, methanol, mercury, ethanol, hexane, and so on. And I've written down their heat capacity as per milliliter of liquid. It seemed to be reasonable to consider the same volume of liquid. How much heat do you need to heat up a given volume of liquid? And all of these, on a scale where water is 1, all of these other liquids are less than 0.5. So it's really unusual to find a liquid that water is quite unusual in that sense. And compared to many other liquids, it's got this very large heat capacity, and that's something that we'll see a bit more in a minute. Another thing that is quite striking about the way water is if we look at the elements that surround oxygen in the periodic table. So we've got carbon, nitrogen, fluorine, silicon, phosphorus, sulfur, and chlorine. They all have hydrides: CH4, methane, notorious greenhouse gas; nitrogen, ammonia, NH3; fluorine, hydrogen fluoride; silicon, that has silicon hydride, SiH4; phosphorus, PH3; hydrogen sulfide, quite a toxic gas; hydrogen chloride, hydrochloric acid. But the fact is, they're all gases. At room temperature, at 20 degrees C, depending on which continent. If you're in North America, it's at room temperature. In this country, it's probably the hydrogen fluoride is probably a liquid, but to all intents and purposes, these are all gases except oxygen hydride, what we call water. So oxygen, and the difference is quite marked. As I say, hydrogen fluoride is the highest one, apart from water, and that has a melting point just below 20 Celsius. All the others are way down, minus 50, minus 25, and so on. So all of these materials are gases at room temperature and pressure, but water is very much a liquid, and it doesn't become a gas until at ambient pressure until you heat it up to 100 degrees C. So there's no way around it. Water is quite a distinct kind of material, and it often gets overlooked, the fact that it is so different from any of the other common liquids. Now, before I go any further, I thought I'd just tell you a little bit about my background. Margaret has mentioned about neutron scattering, and this is a lot of what I'm going to show you. We'll talk about. Some of the stuff I will talk about will actually will refer to the use of neutrons to look at the structure of water. But this is a sort of a unfortunate name. The place where I worked is called ISIS now. It's slightly unfortunate due to the other connotations of that word, but of course it is the name of the River Thames, where it goes through when it goes through Oxford, and it's based on the goddess of fertility, or goddess of health, marriage, and wisdom, who in Egyptian culture, who was called Isis. And what it is actually a proton accelerator, oddly enough. It's nothing to do with fertility, fortunately. It is actually a proton accelerator. You basically have a linear accelerator starting a beam of protons are introduced into a synchrotron. They're accelerated up to 800 mega electron volts. That's you know, it's the standard units for high energy physics type experiments. But at the same time, they're pulsed, so that it starts off here as a continuous stream of charge, but when it goes into the synchrotron, it's pulsed into a pulse of neutrons, and they're sent down these lines, these beam lines, to a target station, and the protons impact a heavy metal target, usually tungsten, and what happens there is that the protons hit the nuclei of the tungsten, and they produce neutrons by a process that's called spallation. So we get this pulse of neutrons coming off this target station, and they travel down the beam lines. And if the conditions are right, we can actually time these neutrons as they travel down the beam lines to a whole slew of instruments. And this facility is actually got two of these target stations. So some of the pulses come to this target station, some of the pulses come to this target station, and surrounding the target station are all these different instruments, which different types of spawn off different types of research. So the instruments, I've been involved in a couple of two or three of these instruments in helping to build them and design them. So that's the place where I used to work. Now within that group, we were very lucky. We had our own little what we call the disordered materials group, because there's a whole field of research that looks at materials which are non-crystalline, basically. And these, I won't tell you all these people, but this is the sort of the group that existed in about 2016. At that stage, I used to be the group leader of this little group. We had about three or four instruments that we looked after, plus an X-ray machine, which we also took data on. And by that stage, this fellow, Daniel Barron, my colleague Daniel Barron, was the group leader, and I was sort of kind of slightly peripheral to the whole exercise, and my job was primarily to maintain the software for the group, and so that they could analyse the data and interpret it. And you'll see a little bit of that as we go along. And so that's as it was in 2016. In 2017 I retired, and here I am in 2022 digging manure in a very wet part of Western Wales. I'm not going to tell you anything about that, just to tell you that I have moved on a bit. So if this comes across as have actually gone on a little bit from where I was when I was at ISIS. Right. So we come back to this question about anomalous water. Now I talked a little bit about heat capacity earlier. There's another quantity which I don't know whether you're familiar with it, but a thing called the compressibility of a material. Compressibility, it's a relatively simple idea. If you take a volume of material you apply pressure to it, it will generally speaking get smaller. That's almost universally true, that if you pressurize it, it gets smaller, it becomes more dense. So, and the amount by which it does that per unit of applied pressure is called the compressibility. Now, most materials, when you cool them down, the atoms are jiggling around like this. As you cool them down, they occupy less space, and that means that they become less compressible. But once again, you find that water is different. Water doesn't become less. It actually, as you cool it down, we're starting here at about 40 degrees Celsius, we cool it down, and the compressibility increases. Now that's a bit odd. That has got to be weird, if anything is weird. And it goes on up. This particular pair of people, Robin Speedy and Austin Angel, they published this data in 1976. So this isn't anything new. It's been known about for a very long time. In fact, I think people knew about this compressibility increase even much earlier than that even. But this was the sort of the definitive result. And what they did was they fitted what's called a critical exponent to these data. I won't go into the details. I can't begin to talk about critical exponents in great detail here, but there's basically a very simple formula that relates, basically try to relate the compressibility to some sort of universal behavior associated with critical points. And it's this is the temperature, this is some sort of characteristic temperature, -1 to some power gamma. And the important thing to note is that this temperature, and they basically fit this equation to those data, and what they showed was that there's a sort of characteristic temperature associated with this data. Oof, is it all right? There's a characteristic, is that me making some noises? No, I don't know. There's a characteristic temperature associated with these data, and it's about 228 Kelvin, which is, I think, of order minus 45 or something. Somebody else can do the calculator. Minus 45 Celsius. So they couldn't actually measure that. You can't actually measure, because to get these data, you've got to create supercooled water, and it's quite. Water does supercool quite a lot. It goes. I think the lowest that's ever been reached is about minus 40, but it does supercool. But that's still quite a difficult experiment to do, and they couldn't go any lower. So they fit this equation. They came up with this sort of seemingly like a characteristic temperature, 228 Kelvin. They didn't actually, at that stage, they didn't suggest this was actually a true critical point in the sense of the gas-liquid critical point. But there was this suggestion maybe that there was some sort of critical behavior or some sort of mechanical stability in the structure of the water. So that was one of the speculations that started to emerge at that time. Now the interesting thing is that if you do the heat capacity, the same thing as I talked to earlier about, I remember I was saying that the heat capacity of water is much higher than the others. This is a slightly bigger temperature range. Apologies, I've changed the units. I'm afraid this is carelessness on my part to a certain extent, but again, the heat capacity initially, starting from very hot water, this is near 100 degrees C, it initially decreases in the way that you might expect. As you cool it down, you expect the heat capacity to go up, and then it goes up again, just in the same way as the compressibility. And actually, you discover if you fit this to the similar kind of critical exponent, you get a similar temperature, 228 Kelvin, or minus 45 Celsius. So this is a bit, there's obviously something going on here that is very strange. Well, these particular facts have caused an enormous amount of debate over the years about exactly what's going on here, why, what's going, what's the mechanism here, what's happening in this system, and. In 1992, a group at Boston University, led by, it's actually a fellow called Gene Stanley, who is an eminent US physicist. He's actually written a book on critical point phenomena. He had a student called Peter Poole working with him, and they were running some computer simulations of water. And they used a particular model of water I won't bore you with what that means, but it was called ST2 model. It was one of the first models of water that ever been invented. And what they observed, and they calculated the phase diagram of the liquid, so we're dealing entirely in the liquid phase here, over a range of pressures here. So, I mean, they've actually got negative pressure on their diagram. When you're doing computer simulation, of course, you can do all sorts of crazy things like having negative pressure. Negative pressure simply means essentially under tension as opposed to be under pressure. What they observed, however, was that as you lower the temperature, so this is the highest temperature at the bottom here, as you lower the temperature, these are basically isobars at each of these, sorry, not isobars, they're isocores at each of these temperatures. They observe these kinks in the pressure. And when they get to about 235 Kelvin, it's more or less flat. Now, I don't know how many of you have studied the van der Waals equation of state when you were at the university, but you may remember that it's got it shows a phase diagram where the isobars sort of level out at one particular condition, and when that happens, that's called a critical point. And so what these guys were proposing was basically that actually water, under these very cold conditions, it actually separates into two liquids. Now, that's a concept that is quite hard to get your head around, and it was quite controversial at the time. Let me try and sort of talk about this a little bit more. So, I'm plotting here the temperature going down here, again at the mixing units. This is now Celsius, so 0 degrees is here. We're going down as low as minus 90, and this is pressure. And what we've talked about mostly so far is this point, essentially zero pressure. We're talking about bars, which is basically an atmosphere, so we're basically at 1 bar on a scale which is going up to 3,000. So, you know, it's basically zero pressure. The ambient pressure on this scale is basically zero pressure. And you can see that this is the melting point, naught. And if you're lucky, you can supercool water down to about minus 38 or something. But you can't go much lower. And every time anyone tried to go any lower, the water would it doesn't matter how pure the water was, it would spontaneously crystallize. And so this point was called the homogeneous nucleation temperature, because basically you just couldn't go below it, and it would just, you know, it would just instantly freeze. It didn't matter how clean it was, how we got all the impurities, it would always freeze. Now the interesting thing is, when you and I don't know how many people are familiar with this, when you pressurize water, the melting point goes down quite a lot, and that's yet another anomaly that we can talk about. Because most materials, when you pressurize them, the melting point goes up. You know, it gets harder. It's more likely to crystallize under pressure because the atoms are pushed closer together. But not so in the case of water. In fact, you can go all the way down up to 2,000 bar, and at that point, the freezing point is around about minus 22 something Celsius. So it's quite a big change in the freezing point. And so that's that line there is essentially the melting. Now, of course, underneath this, when ice forms, the crystalline forms, you get these different phases. So this particular pressure, this is the transition from ice 1 to ice 3, and of course that line changes, and it now becomes a positive slope. So once you get to ice 3, the melting point increases with increasing pressure, as you might expect. But the other thing that is observed is this homogeneous nucleation temperature falls drastically. It goes right down to minus 90. So when you get to 2,000 bar, you can really supercool water a lot if you're clever at doing it. Okay, well that's all right. So where does this second critical point idea come from? Well, first of all, I should tell you that it had in the 80s, early 80s, it was already observed that you could in fact have amorphous forms of water. Now, I don't know how familiar you are with the concept of amorphous material, but of course common glass, the material you're looking out through your windows, is an amorphous material. And when I say it's amorphous, it has no long range order, so there's no crystallites in it, there's no long range structure in it, but the atoms are still disordered. There is a structure, but it's a disordered structure. You'll see a bit more of that as we go through. Now, in the case of water, of course, water is different from everything else, as usual. And there's actually two forms of this amorphous ice. You can have a low-density amorphous ice, and you can have a high-density amorphous ice. You basically compress low-density amorphous ice up to several thousand atmospheres, and it converts to this high-density amorphous ice. And that transition has been studied enormously, a huge amount. And although even now there's some controversy, I think there's fairly strong evidence that you actually do see what's called a first-order phase transition between low-density amorphous ice and high-density amorphous ice. So there is actually some sort of phase transition between these two forms of ice. And again, if you want to learn about that, there's some absolutely beautiful work done by a fellow at Innsbruck, whose name has escaped me just at this moment, but Thomas Lerting, his name is, that's right, and he's done a huge amount. So the idea of this second critical point is that we imagine, ignoring for the moment we can't actually make liquid water under these conditions because it's already crystalline, we imagine that there's actually two forms of liquid water: a high density liquid analogous to the amorphous phase, the glassy phase, and a high density phase, and we have actually a relatively sharp transition going between these two forms of water, and it ends at a critical point, what's called a liquid critical point, and above that we just have one phase. Just like when you have a liquid, you bring it to a boil, it forms a vapor. If you heat it up enough till it reaches its critical point, then you only have one phase. You only have a single phase, gaseous phase. So above this is a hypothetical critical point. You would have a single liquid, and below it you have two distinct liquids. I've put this funny arrow on here, and I'm not sure whether we're going to be able to get to all this subtlety, but there is, of course, associated with every material on the planet, an entropy. Entropy is a very difficult concept, especially even for people who've been in the field a long time. And basically what it tries to do, it tries to measure how difficult it is for a material to heat up. When you apply energy to it, how difficult is it for it to become warmer? And the important thing, and normally when you pressurize things, because they're being pushed together, they're becoming more structured, the entropy normally would be regarded as going down. Unfortunately, again, water breaks that. Not water, but this theoretical model of water breaks that tradition. What it proposes is that the entropy of low-density water is lower, because it's the inverse of that, than the entropy of high-density water. Normally, entropy falls when you pressurize something. In the case of this transition, it would have to increase, and that's again a bit odd, to put it mildly. But I don't want to dwell on that too much. We'll confuse the picture. Well, needless to say, this idea was very hotly contested by certain people, and the most notable of them was a fellow called David Chandler, who at that stage was at Berkeley in California, University of California at Berkeley, and he had a very brilliant student called David Glimmer, and the two of them worked on this problem about this liquid critical point scenario, and they produced a couple of quite this is a picture. Sorry, I'll come back to this, but this is a picture of. This is David Chandler on the left. Unfortunately, David passed away a few years ago. He's no longer with us, but he was a brilliant guy, absolutely superb. He was actually a physical chemist rather than a physicist, but he had a brilliant understanding of the physics of fluids. And this is Gene Stanley, the person who made the original proposal about the critical point. And these two had a bit of a shebang about this. They didn't disagree. They didn't agree with each other at all. And David Chandler was quite hostile to this idea that water had a second critical point, whereas Gene Stanley was very, very keen on it. And it was very notable that when you went to conferences, these two basically didn't talk to each other. They literally they would not talk to each other. And both of them talked to me about the other. I actually had interaction. I had interactions with both of them, and they say, "Well, that David Chandler, and that Gene Stanley, he's this nutcase, and it was really quite aggressive sort of talk at times. But anyway, they're both lovely guys. I mean, there's no question about it. And they produced a couple of papers in 2011 where this is the Chandler group produced these two papers where they basically said the so-called liquid transition wasn't a liquid transit, it was liquid solid transition. Now there followed then several years of intense work by a fellow called Jeremy Palmer, who was at the Princeton University working with a fellow called Pablo de Benedetti. I don't know. He's very well known statistical mechanician. But I think he's actually a chemical engineer rather than either a chemist or a physicist. And he went to this poor Jeremy Palmer. He had to sit on the computer for years to try and understand what these guys had done in their work. And eventually, he actually got their computer code and analysed it, and he produced a series of responses around about 2014, and it was I think it's fairly certain that these guys actually made a mistake. Their simulations hadn't been properly equilibrated for the conditions that they were running, because you're running the simulation at a very low temperature, so of course all the motions are slowed down, so you have to have very long equilibration times in order for this to work. So I think the verdict was, for that particular model of water, that this second critical point seemed to work. The trouble with it is, if you take other models, there's lots of, I don't know how much you follow the literature, but there's a huge number there's probably more than 1,000 different models of water, with different degrees of sophistication, probably more than that actually. And if you run the same kind of simulations on different models of water, you don't always get the same results, needless to say. And in particular, this critical point behaviour, it's all over the place. Some models have it, some don't. Some have it in different temperatures and different pressures and so on. So it's a bit of it still isn't really well known what's going on. Now, so that was the liquid. That was the model, the idea that there is this second critical, based primarily on computer simulation. Now, at the same time, and I have to warn you, I can't possibly do this field justice. I can only give you just a sort of a very superficial summary of what the sort of things that's going on. Was the idea that water, well, I mean, I've talked about the fact that there is this potential for there to be a liquid transition in water. We can't actually observe it in the experiment so far because it's a condition under which real water freezes. It becomes it's below this homogeneous nucleation temperature, so it freezes. Now, even as long ago as the 1880s, Röntgen, who was the guy who discovered X-rays, he proposed the idea, because he was quite a generic sort of person, he proposed the idea that water was actually a mixture of two liquids. So with ambient water, not just this very cold water, but even in the ambient water, it was a mixture of two liquids. And this idea has stuck around ever since. There was a famous spectroscopist, George Walrafen, absolutely convinced that water is a mixture of two liquids. Another chemist, Wills Robinson, he published several papers on this whole business, analysing all sorts of different data. He claimed it was a mixture of two liquids. The most powerful one is this paper that was published in 2012 by a group based on a fellow who's, I can't remember his affiliation, but he's basically an American scientist with I think Russian origins. And I'll say a little bit about that. Probably forget about this last thing because it sort of counteracts it a little bit. Let me just talk about this mixture model, this one I was talking about, Holton and Isimov. Now, what they proposed was something that is a bit weird. I don't know, again, how much chemistry you guys are familiar with, but there is a phenomenon in chemistry. If you take two liquids, depends on which kind of liquids you have. You take two liquids, you make a mixture, and either they mix or they don't mix. And if they don't mix, there's a good chance if you heat it up or you cool it or you do something to it, they start mixing. So this phenomenon of liquids possibly going through some sort of liquid-liquid transition is not unknown. It does happen quite particularly in lots of chemical systems, and I think is actually exploited in the chemical industry to quite a large extent. So they took this idea and said, well, what happens if we imagine we've got these two liquids we've got these two states, low density liquid, high density liquid. They don't actually tell you what they are, so they don't actually say anything about what the physical form of these states is, and we make a mixture of them, and adjust the parameters of the model. They actually demonstrated they could get an amazingly good agreement with the measured properties. Now, this is just one of those plots. This is the density here, going up this scale here. Don't worry about the actual units. I mean, you can see it's in kilograms per meter cubed, so 1 gram per centimeter cubed is 1,000 kilograms per meter cubed. And this is the temperature. And what the dots are, these are all the known data about the density of water as a function of temperature and pressure. And the lines are what their model predicts. So, for example, this line here is 0.1 megapascals. That's essentially ambient pressure. You can see that the density, when you cool the water down, initially rises. It initially increases, excuse me, and then of course it reaches a maximum about 4 degrees Celsius, and then it starts to fall again. So this is the classic behaviour that we see, the so-called anomalous behaviour, and it falls down. Now, as you increase the pressure, this maximum moves to lower temperatures and eventually disappears. But their model is able to reproduce that trend remarkably well. And it's been it's been looked at several times, this model. And the interesting thing is what they observe when they try and fit their data is a critical point in the model, which is 227 Kelvin, which is remarkably close to this number that the people found when the heat capacity and the compressibility data, it was about 228. And it's also relatively mild pressure. It's a 30 megapascals, so that's about 130 atmospheres. So it's not a huge pressure. The computer model had come up something like 2,000 atmospheres. Don't know if it shows it here, does it? Yeah, it was. Well, no, it doesn't show it there. Anyway, it doesn't matter. But it is much lower. So, and this is much more in keeping with the compressibility and the heat capacity. And so the thing that sticks in the throat about this model, it's all very well, it works really well, but we don't actually know anything about what these liquids actually look like. And there has been a huge amount of work using computer simulation to try and identify these two species in the water. But I'm actually very sceptical of that, and I wrote a paper, actually since I retired, I wrote a paper on this, why I don't believe that there's any evidence yet of actually there being these two distinct species present in liquid water. I'm very much a person who believes there is only one species in ambient water. I mean, I can accept the idea that if you cool it down enough, you might get a transition between two states. That's perfectly right. But once we get above this liquid-liquid critical point, then there is only going to be one state. And what I was going to do now, hopefully, well, that's just fitting some data just to show you again how well they fit the data. What I was going to do now was actually tell you a little bit about what I've been doing with the neutron aspect. So this is because it does actually relate quite closely to the previous topics. Now, this is a machine. This is one of the diffractors. Is in fact one of the most recent ones. This came into operation in 2009. So I already said a little bit about how we produce neutrons. We have this beam of protons hits a target, produces a pulse of neutrons, and then there's a beam line from a target over here somewhere, where the neutrons are transported to a sample area. So you have a series of apertures and things to control the neutron beam to focus it down. Neutrons, of course, are very penetrating, so you have to have huge amounts of shielding around them, because you obviously want to make it safe for people to live in the environment around it. So there's a large amount of steel around these beam lines, and then that's surrounded with wax and borated wax, because boron is a good absorber of neutrons. So the experimenter puts his material he wants to look at in this position here, and then the neutrons are scattered by the material into a whole vast array of detectors all around it. And the more detectors you can get around the sample, the better, because it gives you more and more counts. And neutrons, being what they are difficult to make. You can't make anything like the intensities that you can with an X-ray beam, so we have to try and make optimal use of the neutrons that we do produce. I'm not going to say what that is all, how it all goes through, because it takes so much too long. The important thing to bear in mind is that what we're doing here, the neutrons start off from some target down here at the particular point of time, but they've all got different velocities, and so they travel down the beamline at different speeds. And that means that if we have clever electronics associated with the detectors, we can actually time the arrival of the neutron. So as long as the clock starts when the pulse of protons hits the target, we can actually time the arrival of the neutrons, and from that time we can calculate their energy. So if they've got an energy, they've got a wavelength, a de Broglie wavelength, just like any quantum particle. And from the wavelength, we can calculate this quantity that we call Q. Some people call it K. It doesn't really matter. The main thing is that it's a function of two variables. It's a function of the scattering angle. So you've the beam of radiation coming in here, it's scattered into some angle, and that's called 2 theta, which becomes a single theta in this definition of Q, 4 pi sine theta, divided by the wavelength of the radiation. And there's actually two ways of doing these experiments. You can either scan the detector as a function of angle, keeping the wavelength fixed, or you can keep the detector fixed and scan the wavelength. Or in the case of the Nimrod machine, we actually have a whole range of different angles, but we also scan the wavelength, so we can get lots and lots of neutron counts in our machine. But the main thing is the data is a function of this variable Q. And so it's almost like a universal variable. And the reason for that is that the meaning of the data, the interpretation of the data, is based on this value Q. It doesn't matter whether you use sine theta or use lambda, it's the value of Q that is important for the interpretation of the data. Right, so this is an example of the sort of data. So I'm putting this Q here, along this scale here, in some units. We're still old-fashioned enough to use angstroms rather than nanometers, but that's beside the point. And what I'm showing you here is why we use neutrons to do this experiment. So at the bottom, I'm showing you what looks like if we use light water. This is the standard water that comes out of your tap. Well, of course, it has to be highly purified, but nonetheless, it's the water that comes, it's basically standard water. This curve up here is D2O, that's heavy water. Maybe you're familiar with the idea that hydrogen has got 3 isotopes, hydrogen itself, deuterium and tritium. Deuterium oxide looks, to all intents and purposes, like ordinary water, but it's got a mass of 2. The deuterium's got a mass of 2 compared to the hydrogen's got a mass of 1. And what you'll see is the pattern from D2O, heavy water, is completely different. It's actually almost inverse compared to light water. Now the reason for that is simply that the neutron interacts with the nucleus, and the deuterium nucleus has completely different scattering properties to the proton. So we get a different pattern. And that's really useful, because that means we can actually start to investigate these curves. Now, what I'm showing you here is essentially a half and half mixture of heavy water and light water. And this is what's called a null mixture. I won't bore you with the details. It's basically a way of cancelling out the scattering from the hydrogen. And you can see you get these different patterns. That means we've got a very nice handle on the correlations that take place in the liquid. And this is something that I've exploited, a very large chunk of my career I've exploited. I've also shown you on the top what happens with X-rays when you put one of these, a sample of water in an X-ray machine, you get some curve like that. This actually should in principle look very much like the null water, because it's basically X-rays don't scatter from hydrogen very strongly, so it's almost purely the oxygen scattering that causes these ripples. The main thing is to show you is that you get this very ripply sort of pattern that goes out as an increase in Q. So our task is to try and interpret that pattern to learn about how the molecules are arranging themselves in the system. Again, I can't possibly go through all these the ramifications of how we do that. But basically, I talked a little bit about computer simulation, using computer simulation to build models of water. Well, we basically try and do something similar here. We basically define our molecules in some sort of sensible way. We start off with one of the typical interaction potentials between water molecules that are used in the literature, and then we use the diffraction data to perturb this potential, to try and improve it so that when we simulate the data we get as close as possible. And you can see some lines underneath these data. These lines are attempts to do this simulation, this refinement of a structure, of a model structure, to try and get it as close as possible to the data. It's not possible to do it perfectly. You can see there are some discrepancies, but we do capture to a large degree the correct shape of these curves. I could talk about discrepancies if you wanted to, but it's a long talk, so I don't want to spoil it. So what does that look like? Well, the first thing that comes out of that are things called correlation functions, and this is where talking about liquids gets quite hard, because people don't normally think in terms of correlation functions. But actually the concept is actually very familiar to you, except that you just don't know about it. If you're in a busy shopping, the best example I can think of is if you're in a busy shopping precinct, surrounded with people around you, you might think, well, I can just go anywhere in this shopping, I can go around. Well, actually you can't. If you think about it, you can't walk into people, you can't walk through people. So if you want to go from A to B, you're going to go some sort of wobbly path, avoiding the people. Because it's a very densely populated situation, you've got lots of people there, that means that your motion is actually correlated with their motion, because depending on what they're doing, that affects how you move. Well, exactly the same thing happens in the case of a liquid. We have these correlations between the molecules, and because they're relatively densely packed, you discover that you can't actually have atoms on top of each other, because the electronic forces come together and say, no, you can't, the electrons, you've got Pauli repulsion comes, the exclusion principle comes in and it stops them overlapping. So you have this region where there are no correlations, essentially zero in this low distance region, and then you get a peak because, well, it's just the way things correlate. And if you did this analysis of a crowded shop, you would see a curve very similar to this. You'd see a peak. That would be the people all around you that you're nearest to, and then you would see it decaying as a function of distance, because obviously as you go far enough away from somebody, there is that you're not correlated, that you're not interacting with them in any way. Well, because water has got two atoms, it's got two types of atom, oxygen and a hydrogen atom. There's three of these site-site correlation functions in the case of water. There's an oxygen-oxygen correlation, there's an oxygen-hydrogen correlation, there's a hydrogen-hydrogen correlation. And it turns out that all of these three functions have quite a very distinct structure. We've been measuring this thing now since about 1982, so it's been going a long time, 40 years now. These functions don't really change. Every time we measure it lots of times, every time we measure it, they come out pretty much the same each time. So I think we're fairly confident now that these are the right functions. And it's very strange. The last time we published this, I think it was about 2014. I can't remember the last time, but at the same time, it turned out a completely independent team in the States, using the advanced photon source at the Argonne National Laboratory, they produced an X-ray pattern which was almost exactly, it wasn't perfectly aligned with the neutron pattern, but it was extremely close. And so I think these functions are fairly well established now. And of course, they're really important for people who want to develop models of water, because it gives them a sort of yardstick to test their models against. If they can get these three functions right, they know they're into a good thing. But what I want to bring out today is something slightly different, is that because there's three of these things, they actually give us some information about water which you can't get any other way. I mean experimental information that you can't get any other way. Let's just look at this oxygen-oxygen term, for example. This is the correlation between the centre of the oxygen atom, of one oxygen atom, and the centre of another oxygen atom. So that's essentially the centre's correlation between these two molecules. And it's got this big peak in it, and it's got a secondary hump and a third hump and so on, because it decays away and there's no long-range correlation. So it's definitely not a crystal or anything, it's definitely a liquid. These correlations die away. When we look at the second one, which is the oxygen-hydrogen, now we're sitting on the oxygen atom here, and we're looking at the hydrogens. You notice it's got these two peaks, whereas this has only got one peak in this sort of distance range, around about 2.8 angstroms. This has got two peaks. And that can only mean one thing. That can only mean that the two hydrogens are correlated quite distinctly with this central oxygen. So one of the hydrogens is closer, that's that one, and one of these hydrogens is further away, that's that peak. And that means that this molecule is quite strongly oriented. Because this is quite a sharp, well-defined peak, this molecule is quite strongly orientationally correlated with the central oxygen atom. When we come to the third one, which is the hydrogen-hydrogen, we've now got two hydrogens on one molecule, two hydrogens on the other, so there's a total of 4 terms here, but again we've still got quite a pronounced first peak and a second peak. And if you start thinking about how triangulation works, if we know all these distances, we can calculate the relative orientation of this molecule relative to that molecule. You can't do it with this one, because this only tells us the correlations with the centre. So I could have put this molecule anywhere around this one, so long as that hydrogen's pointing towards it like that, then it could be any one of those positions. But with this information, I can actually be quite specific. It's got, if I combine that information with that information, I can have a reasonably good idea of the relative orientation of the two molecules. And that's really crucial if you want to try and understand water. So, just to sort of fill you in a bit further, what we do with that information, with those three, we build a model of the local environment of a water molecule. So if you imagine this is a water molecule at the origin, we're going to plot out where the neighbours are around in this shell around it. And it's got a very characteristic shape. To do this, of course, the trouble is I've got to plot a density as a function of 3 dimensions, distance, and if you think about what you've got to plot, you either think of it in terms of x, y, and z, so you've got an x coordinate, a y coordinate, a z coordinate, or you've got a polar angle, theta L, phi L, and a distance. But the point is you're trying to plot a density as a function of 3 coordinates, and that's physically impossible to do. And so what we do is we use what's called a surface contour. So we imagine drawing a surface around the highest. We choose a level of the contour. This is what's called a 1% level. So we choose the highest. We choose the region which surrounds the highest density, and we plot what that is. And it looks like this. So here's our central water molecule, oxygen and 2 hydrogens, and there are 2 lobes, one opposite each hydrogen. So this would be characterized as so-called hydrogen bonding between the oxygen, the hydrogen here and a neighbouring water molecule. As we lower the contour level, so we're enclosing more and more of the density of the water, you see that a second pair of lobes start to appear underneath the top one. So we've got these 2 top lobes here, one opposite each hydrogen, and then you get a second set of lobes underneath. And in ice, that would be classified as the lone pair. Sometimes people talk about lone pair electrons and so on. This is sort of causing. This is essentially the corollary of this one. This hydrogen looking at. Then there's a water molecule here with this hydrogen looking at it, and it gives you this sort of tetrahedral structure. And tetrahedral, of course, is what makes ice ice. It's basically tetrahedral structure. So that's all very well, and eventually when you get to something like about 12% of the density, you see that the top two lobes stay completely separate, but this bottom lobe has become continuous. So it's not 100% symmetric, this distribution. It is a bit asymmetric. The top is different from the bottom. Some people call this a nappy plot because of the similarity with the baby's nappy, but that's another story. Now, if we keep on going down in raising the lowering the contour level, you see a second shell starts to form, and the second shell is more or less in antiphase with the first shell. So that's, and as far as I know, I don't know any other material that does it, has such a distinct structure. We've looked at quite a few of the liquids, like the ones I listed near the beginning, and none of them have such a distinct structure as in the case of water. Okay, so that's the picture of water. That hopefully that will be a sort of one of the take-home messages. That's what water looks like at the molecular level. But what I should tell you about, I'm only plotting 3 dimensions here. I'm plotting the positions of the neighbouring molecules. What I'm not plotting in this, and I don't know how to plot, is the orientation of these molecules. Now, I told you that these are a function of distance and 2 polar angles. That's three variables. But to actually define the orientation of a water molecule itself, you need another 3 dimensions, the so-called Euler angles, which define the relative orientation of this water molecule. So actually, you know, if you really want to understand water, it's a 6-dimensional problem. And that fact, I'll allude to it again, doesn't always sink home to a lot of the people who study water. Now, some experiments we did with a colleague from the University of Rome was actually pressurized water, to try and do this now under pressure using the conditions that, you know, similar to the sort of things that the people doing the critical point, the second critical point idea we're talking about. So this is essentially, this is actually slightly below the normal melting. It's about -5 Celsius, but as I said before, if you pressurize water a little bit, the melting point goes down, so you can do it in the stable liquid. So that looks pretty much the same as the ambient liquid. It's not tangibly different. We now pressurize it to 2,000 atmospheres, and you'll notice immediately that the very characteristic behavior, the first shell stays pretty much the same, it doesn't change very much, but the second shell collapses inwards. You get almost like a breathing motion as you pressurize the water. And that, of course, is what brings out the real aspect of what makes water so different, is that, and it explains why you can have this strange behavior when you cool it down, the density keeps decreasing. Basically, when you cool it down, these lobes pull out, they come out, and so that makes the density fall. It becomes a lower density, even though you're cooling it down. And as you increase the temperature, the angles between the molecules become more random, and so it collapses inwards. We also went up to 4,000 atmospheres and 4 kilobar, and you can see that it collapses even more. Now, I haven't got time to go. How much time have I got now, am I? Sorry, I'm
-2.
-2, my God. Well, I haven't really, I mean, I wasn't going to say much about this anyway, but of course we have studied water in lots and lots of different systems, as Margaret has told you. And this is what we observed. One particular experiment, I'm just going to show you one experiment. This is pure water again, the same as I just showed you, but then we did an experiment of magnesium perchlorate. This is a collaboration at the University of Leeds. And the interest there was because, I don't know if you know, but they've discovered there's quite an abundance of magnesium perchlorate on the surface of Mars, and so the speculation is that maybe water can, and the point is that when you dissolve magnesium perchlorate in water, the melting point goes down enormously. It goes down to about 200 Kelvin, and of course it's very cold on Mars. So the idea is you could actually imagine having liquid water on Mars in the form of a magnesium perchlorate solution. And we've actually studied quite a few different ionic solutions using this same method. And depending on which particular pair of ions, you get exactly the same sort of collapsing. That's the effect of pressure. That's the effect of this magnesium. A huge collapse in the second shell structure. Anyway, I don't have time to go on. Probably I should skip this bit. Anyway, I'll try and summarise it very, very quickly. Basically, using the same data that I've already talked about, we can go another step further, and this is where it gets quite complicated. I've talked a little bit about entropy, Why do I talk about entropy? Well, we talked about specific heat. Specific heat is essentially the rate of change of entropy with temperature. And there's several curves here, which I can't really spend a lot of time, but basically you can actually, based on those correlation functions, those site-site correlation functions I showed you, you can actually calculate the entropy of water. And in this paper that I wrote since I retired, I think it was about 2019 it appeared, I actually used the data to calculate the entropy of water. Now to do this you have to calculate, first of all you have to calculate the entropy of an ideal gas, which is essentially free water molecules tumbling around in space, and that's this line here. The red line here, if it's red, I'm a bit colourblind, is what we think the entropy of water actually is. So this is calculated based on the known specific heat and on the assumption that the value at 300 Kelvin is about 70, whatever the units are, joules per mole per Kelvin, but that unit. And then using the reconstruction of the structure that we used from the neutron data, we actually calculated this entropy, and you can see that it actually follows the experimental curve surprisingly well. It doesn't quite reach it, and that's a sort of technical thing because I'm only dealing with pair correlations, site-site correlations, and strictly speaking, you should deal with many body correlations as well if you're going to do it properly. But you can see it gets pretty close. There's some uncertainty about it. And what's noticeable is that we also had some data on these amorphous phases of ice that I talked about, and it ends up very, very low when you go down to the liquid nitrogen temperatures at these amorphous phases. The important thing to notice is that this point, there seems to be where the heat capacity is increasing. This seems to be the point where this magic temperature of 220 something Kelvin appears. So there seems to be some sort of something happening in that region. Well, okay, I've got to get on. This is just one more slide here. This is another colleague who based at the University of Stockholm in Sweden, Anders Nielsen. He's actually a solid state physicist, but he's done a huge amount of work with X-rays. And the amazing experiment that he tries the most difficult experiments on the planet. So he's way out of my league completely because he really tries difficult experiments. But what he does, he uses an X-ray laser. He generates very tiny micron-sized droplets of water. He puts them into a vacuum, throws them into it, and they cool evaporatively. So they cool very quickly and suddenly thrown into a vacuum, and they cool quickly. He then shines this X-ray laser at them, and he captures the structure. And because it's so bright, the X-ray's got so much intensity, he can get a diffraction pattern from one drop in one pulse. So it's incredibly exciting work. But the thing that's neat about it is, of course, if the droplet crystallizes, remember we're going now down into the region where water automatically crystallizes if it gets too cold, he can eliminate that from his data set. So he just eliminates it because he can see it. As soon as it crystallizes, you get sharp peaks in the diffraction pattern. He knows it's no good. So he knows that he knows that he's only looking at the liquid. Now, I have to say there's a lot of controversy about some of this work, so I can't say too much, but in the most recent paper, 2021, he's actually tried to calculate this, using this technique. He's actually measured, or claims to have measured the heat capacity, and lo and behold, what he observes is he sees this rise, but it goes through a peak at about 220 something, 228, 229 Kelvin. So that's really exciting if that's right, because it kind of reinforces this idea that maybe if only we could eventually get into that region where into the region where it's where water is unobtainable as a liquid, we can only get in there, we might actually observe this critical point. So that's pretty much it. Sorry, I went the wrong way. I'll just try and quickly summarise. I've written this quite carefully. I said neutron data are not inconsistent with the possibility that water has a liquid critical point. And the reason for that is that it seems to fit in with this idea that there could be a transition at some point. I say not inconsistent. If I'd said if it was consistent, then people would go away and they say, oh yes, he's saying that there is a second critical point. Well, I don't know that. The second has not been observed. So all I can say is that the data are not inconsistent with the idea that there might be a liquid-liquid critical point. But I have to emphasize, as I say, this critical point has never been observed directly. Nobody's actually seen it. I've tried to emphasize that I think water has to be regarded as a six-dimensional object. And if you don't deal with the full dimensionality of the problem, I don't think you're ever going to solve it properly. Now, how you deal with that, I've got no idea. I'm not a theoretician. I imagine it's going to be extremely difficult because it involves orientational degrees of freedom. The idea that water is a mixture of two types, the reason why I find it difficult to accept is that I think it ignores the six-dimensional character. It basically, it's a model by analogy. You're taking an idea that you can see some particular behaviour in a particular type of system, and then you translate it to the water case, but you don't actually build in the fact that it's a six-dimensional system. And I suspect if you could only do this properly, you might discover that a lot more about why water behaves the way it does. The neutron data I've talked about, they've been very widely used by all sorts of people to develop their preferred potential, the interaction potential for water, and of course that's important to try and understand. And there is little doubt this story will run for many years yet. So finally, I just have to, I mean, there's so many people here, I should be acknowledging that it's impossible to put it into several slides. But I do have to acknowledge my PhD supervisor, John Enderby, who was at Leicester at the time, as Margaret said, and he eventually moved to Bristol, where he was head of the department for many years, and he actually became, of course, president of the Institute of Physics for a while. John was an absolutely amazing character. I can't say enough about him, and he's probably one of the most inspiring physicists I think I've ever encountered. He gave wonderful lectures, but he was very disorganised. And he always ended it with a question. He always left you coming away from the and he just led you on. I must go and find out about that. I must, every lecture, even if it was just some boring solid-state physics, he'd always end it on a question. Peter Agustaf was a neutron physicist, originally at Harwell, but he moved to Canada in 1970, and I worked with him as a postdoc. Again, absolutely brilliant guy. He was actually, I think, trained as a mathematical physicist, but absolutely brilliant. He taught me neutron scattering, basically. It was because of him that I managed to build all these neutron machines. And then I've got three more recent colleagues. Maria Antonia Ricci from the University of Rome 3. I've been with her, worked with her now for, I can't remember, I think 87 maybe was the first experiment. We did some work on hydrogen iodide or something. She's been an absolute stalwart. She's often the driving force behind getting some of this work done. Daniel Barron is my colleague at ISIS. He was been very influential in driving the development of the technique. And finally, Lorna Dugan at the University of Leeds. She's been very instrumental in building in the biological aspects of some of the work. Anyway, that's enough from me. I'm sorry I've gone over my time a bit, but I really appreciate the opportunity to talk to you. Thank you.